Hello everyone! In this video we will continue to examine topic 2.1 motion, and in particular we will begin to discuss the concept of instantaneous and average velocity. So, when objects accelerate, their velocity changes, and we're going to discuss this in more detail later. Acceleration will be a very important concept for us. But the general idea is that in a particular time interval, right, if I graph my position versus my time, then I might go slow for a little while and then go fast. And the final result of that is a smooth curve on my position time graph. Okay, a smooth curve on my position time graph. So if that position time graph is curved, then my velocity is changing. And we can define a number of very useful concepts with that. But it is important to sort of disambiguate a few of them. And the general idea here is if objects are accelerating and the velocity changes, then we actually need more than one concept related to velocity. For example, I could ask for what is known as the instantaneous velocity at any particular point. That is the velocity right now. Okay, it's the velocity that your speedometer in a car is going to show. It's going to show you how fast you're going right at this particular moment. Whereas you might also be interested in the average velocity over a time interval. So an interval in which you go slow and then you go fast and then you go slow again, all right? You might want to know the average velocity over that particular interval. And the key is to recognize that the average velocity is always the total displacement over the total time. Notice this is very similar to our definition of velocity, or a calculation of velocity, when velocity is constant. Because, of course, if velocity is constant, then the average velocity is just the velocity the whole time. But we retain this definition, that is the total displacement over the total time, but this is now exactly what it is to be the average velocity. This is what we mean when we say the average velocity is this total displacement over the total time. And therefore, V average is equal to delta x over delta t. Notice that total time here is some time interval, delta t, some t final minus t initial. Okay? And the instantaneous velocity, by contrast, is defined to be the velocity at a particular time or a particular moment. It's the velocity at a single instant. And it's not obvious that there is such a thing, right? So if velocity is related to some kind of change in displacement over some kind of change in time, what does it mean for it to be a particular moment in time? Well, as you'll see in calculus, there is a way to sort of narrow in on this particular idea using what is known as a limit. Okay, and so perhaps you haven't seen this before, but the general idea is that we are going to take our delta t in our average velocity definition, and we're going to shrink it down. Okay, we're going to shrink it to become smaller and smaller and smaller until we can figure out what the velocity is at a particular point. So take a look at this graph here. The average velocity is given by the slope of a line connecting the 2 points, okay, because it is delta x over delta t. So if I'm looking at this position time graph, this is the position time graph of an object accelerating, and in this case, speeding up, speeding up, speeding up, speeding up, in particular at a constant rate. Notice that my average velocity can be calculated between any 2 points by simply taking the delta x divided by the delta t. Notice that that will also give a slope, right, of this line right here. So the average velocity is a calculation, or can be found by taking the slope of any 2 points on this curved position time graph. And now consider what happens if we want to find the instantaneous velocity. That is, we want delta t to be so small, okay, so small that this line is as close as possible and in fact equal to the point on the curve itself. So if I go from, for example, this blue calculation of the average velocity to this green calculation of the average velocity, you can see that the slope of that green line is a lot closer to the slope of the line itself in that time interval. So I'm going to shut delta t down as small as humanly possible and then figure out what the ratio is of my delta x to my delta t. I can use a calculus concept called a limit to do that as well. So I can find the slope at a point that is tangent to the curve. So I shut my delta x over delta t down, and I discovered that the velocity at this point is the velocity indicated by a line that is exactly tangent to that point. That is, it just kisses the curve. In calculus notation, the instantaneous velocity is just dx dt at a particular point. And if I narrow in here, I could draw a line directly tangent to the point that I'm interested in. So the velocity at this particular point on my position time graph can be found graphically. How do I do it? I take my ruler and I line up a line exactly so that it is just barely touching this curved line here of the position. And using that, I can then extend it outwards, find my purple delta x and my purple delta t, and then use that to calculate the velocity right at that particular point. I can also use calculus techniques, but this is the technique, graphically, that I'm going to expect you to use in this class. That is, if you're given a curve and you're asked for the velocity at a particular point, where that curve is on the position time graph, you can find the velocity by drawing that line tangent to the curve and then dividing the delta x of that line that you have drawn by the delta t of the line that you have drawn. And in this case, you can see that this particular object is speeding up. How can you see that? We'll take a look at the purple delta x over delta t compared to the blue delta x over t. You can see that the tangent line has a higher slope at this point and therefore is moving at a higher velocity.